Theorem 3.3.3 that we saw proved today is a similarity criterion for two triangles that says if a pair of triangles have one pair of equiproportional sides and the angle adjacent to those sides are congruent, then that's sufficient for those two triangles to be similar. This is the sAs criterion, where the A is capital letter and the S's are small. So the content of the proof that we worked through for 3.3.3 had us use a similar technique to a technique we've used before, where we take the smaller of the two triangles, so-called, and we make an attempt to embed it within the bigger triangle and make an argument that way. The tricky part was that we have to choose carefully what information that we're embedding, what we know we can get away with. So we embedded this triangle using the congruent angle A and D, and defining the point x on the side of the bigger triangle so that AX was equal to DE. So we already have one congruent side, and that's adjacent to one of our congruent angles. The problem is we don't know, at least not right off the bat, how to introduce ourselves to this last point y. And so in the proof, the idea is that we construct y in such a way that xy is parallel to BC. What that doesn't tell us is it doesn't tell us that AY is congruent to DF. That would be wishful thinking. So we chose parallelism here for a reason, because of what it gives us as far as congruent angles. So as with our proofs from before, that parallelism gives us the ability to treat AB as a transversal to these two parallel lines and give us congruent corresponding angles, and likewise treating AC as the transversal to XY and to BC gives us another pair of congruent corresponding angles, and having two pairs of congruent angles in the triangles AXY and ABC is enough to guarantee the congruence of the third angle. This angle here, A, is common to both triangles, so we have three congruent angles, and AAA similarity gives us that AXY is similar to ABC. And that's great because it gives us the equal proportions of all the sides in this pair of triangles. But that doesn't quite get us all the way home yet. So having the equal proportions on all the sides gives us this set of three equal ratios. But we don't care, ultimately, about AX, we don't care about AY, we don't care about XY. What we care about are the lengths in the triangle DEF, so we need to relate those back somehow. And we do that, first of all, by swapping out AX with DE, because by construction, those two segments were congruent. That brings AB over DE into the mix. But where else have we seen AB over DE? We saw it in the original hypotheses of our theorem. That was one of the ratios which we know is equal to the other ratio of sides in our SAS. And so by assumption, AB over DE is equal to AC over DF. And so now we have four equalities that we can play with. And that set of four equalities, we notice that two of those ratios have the same numerator. They both have AC. And because they both have AC in the numerator, the two denominators must be equal. That guarantees that DF is equal to AY, and that allows us to say that those sides are congruent. And now the triangle DEF is congruent to the triangle AXY because we have side, angle, side congruency. So we now know that AXY really is a congruent copy of DEF inside of our bigger triangle. And since we justified why AXY is similar to ABC, that also means that its congruent copy DEF is similar to ABC. And that's just a step of logic wherein we remind ourselves that a pair of congruent triangles, such as AXY and DEF, are in particular also similar triangles. And because similarity is a transitive relation, if one triangle is similar to another, which is similar to another, then the first one is similar to the last one. And so we get the similarity of ABC to DEF. And the second result we saw today was the result of Sss Similarity, that tells us that having three sets of equiproportional sides for a pair of triangles is enough to guarantee those triangles are similar. In other words, equiproportional sides guarantees congruent corresponding angles, which is, again, a bit of a surprise. And this proof also proceeded along similar lines, no pun intended, wherein we take the bigger of the two triangles, we construct points P and Q on the sides of those triangles in such a way that the length dp agrees with the corresponding length AB in our original triangle, and dq corresponds to AC as a congruent copy as well. Now notice, this time we don't know anything about the angles A and D here being congruent. We've just said, whatever this angle here at D is, we're going to pick a point P, which is as far away from D as B was from A, and we're going to pick a point Q, which is as far away from D as C was from A. So that's all that we get. But by substituting dP in place of AB in this ratio, and substituting dQ in place of AC in this ratio, we now get this relationship between the sides dP and dE, and dQ and dF. And that's enough for us to invoke a lemma, 3.3.6, which guarantees that under that circumstance, under the circumstance of equal proportional cutoff, that we get PQ is parallel to EF. So notice how parallel shows up in this argument again, because once we have parallel, we get a lot of other stuff to go along with it. There's still a question of whether we can use 3.3.6 in the proof of 3.3.4. We're going to have to look and see whether or not that leads to a circular argument, especially if 3.3.6 uses this result in its own proof. Then it would be off limits. But setting that aside, that parallelism gives us congruent corresponding angles, dPQ and dEF, as well as dQP and dFE. So in fact, what that does for us in this diagram is, now that we know that PQ is parallel to EF, we have a theorem, 3.2.4, that's enough to guarantee that dPQ is similar to dEF. So now we have a pair of similar triangles in this figure, in the same way that we had pairs of similar triangles in figures like this in the past. The question is, how is dPQ related to the triangle that we really care about, ABC? Because that's left unclear in our construction up until this point. To answer that question, we need to make a congruency argument between dPQ and ABC. And we start that congruence argument by observing that these two triangles already have one pair of congruent sides in DP and AB, another pair of congruent sides in DQ and AC. So one possible line of attack might be to show that that third side is also congruent, and use the SSS Congruency Criterion. So how do we know PQ is congruent to BC? Well, we have to bootstrap our way up, once again, from what we do know into what we're trying to find. We start by observing that because these two triangles, again, dPQ and dEF, because those two triangles are similar, we get the equiproportionality of their sides. So dP to dE is the same as PQ to EF. So now we're bringing in these sides, which we don't know anything about yet. But because AB is the same as dP, we can substitute AB in here. So AB stands in the same ratio to DE as PQ does to EF. But where else have we seen the ratio AB to DE? We saw it from over here. From the assumption in our problem, AB was equal to DE. And so, AB over DE was equal to BC over EF. And so now, comparing these ratios over here, we can make the argument that multiplying both sides by EF, PQ is congruent to BC. And so now in our two triangles, dPQ and ABC, we have three congruent sides, meaning that the SSS theorem tells us that ABC and dPQ are in fact congruent triangles. And therefore, since ABC is congruent to dPQ, and dPQ is similar to DEF, again by transitivity of similarity, ABC is similar to DEF.